So we're going to next look at a very revolutionary experiment when it comes to the model of the atom. And now, looking at this diagram, it's an experiment that's kind of similar to us. It's the double slit experiment, except now instead of using light, we're going to be shooting electrons at high speeds at a double slit. What we would expect is if electrons are particles, and that was the prevalent thought at the time of Bohr's model, is that these electrons still existed as particles. Although with that there are some complications with Bohr's model. Even still with Bohr's model, even though these electrons are at stable states, they should be emitting EMR according to Maxwell's equations. So we should eventually be losing energy. So Bohr knew his model was incomplete, but we still thought electrons were particles. So if we shot electrons at this screen, we would expect them to hit the screen in these two spots if electrons behaved as particles. Now, when we shoot light at a double slit, we end up with this. We end up with an interference pattern, where we have these areas of very bright spots where we have constructive interference, and then these dark spots where destructive interference is going on. And we remember that this is an example of the wave-like behavior of light. Now, when we shoot electrons at that double slit, we don't have them hitting the screen in just two spots. We end up with an interference pattern. And this was revolutionary at the time and really baffled scientists. Scientists thought they had a really strong grasp that electrons were particles because they had a lot of evidence of electrons exhibiting particle-like behavior. Then this experiment came along, and now all of a sudden electrons also exhibit wave-like behavior. This was kind of where quantum mechanics really started to take off. This picture here is in October 1927. This is a conference where all of the brightest minds in quantum mechanics at the time got together to discuss kind of current quantum mechanical theory. You'll notice two guys in there, Rutherford and Niels Bohr. De Broglie is a gentleman we're going to talk about because he actually came up with an explanation for this double slit experiment. Fun fact, in this picture, 17 of the scientists here actually went on to win Nobel Prizes. So a lot of very bright minds at the time. But getting back to de Broglie, he thought about light, and he thought about, well, light can be actually expressed as both a wave and a particle. Now, if light shows wave-particle duality, well, then maybe particles do the same thing as well. And so he came up with this explanation that electrons are also wave particles. So we can actually use the same set of equations for electrons. Here, wavelength is equal to Planck's constant over the momentum. We can use that same equation for both photons of light and also for electrons, which exhibit this wave-particle duality. Now, we notice this wave-like behavior most for particles that are very small, traveling at high speeds. So electrons in that double slit experiment are small, traveling at high speeds, and so we see this wave-like behavior, and it shows up as that interference pattern on the screen. So de Broglie's hypothesis relates the wave-particle duality of electrons to that of photons, where we can use this same set of equations for massless photons and also for things with mass, like electrons and protons, neutrons, etc.